Yeah. I've been doing it. You didn't do it in your own.
For us, all relation conclusions is
Yes, but yeah, now it's super. People like this, okay. But they won't show up. Ah, yeah, for now, yeah, and you can make the here, like this. You will like this, and you move it in your on your screen. Shut up, everyone here, nice. They don't look for let me know if you need to send us off. So we are waiting for the rest of the jury members to be here. Thank you for waiting, Farida. Thank you for being here.
Okay, there is no problem. I'm waiting.
I just saw them. They're gonna come shortly.
Okay.
Thank you.
Faz uma quentinha.
Il y a juste la faute.
C'est bon? Ok, bonjour à tous et bienvenue à cette session publique pour la Soutenance 13 de NADA. Donc, je m'appelle Yvan Barzingzak, je suis prof d'informatique à l'Université Sorbonne Paris-Nord et j'ai l'honneur d'être le président du jury. Okay, donc, je vous présente d'abord mes collègues composant le jury. Donc, nous avons les rapporteurs, M. Julien Aligon, maître des conférences à l'Université de Toulouse-Capitole, et aussi M. Thomas Guillet, chargé de recherche à l'INRIA. Nous avons aussi les examinateurs, Olivier Bourdon, qui est professeur des universités et praticien hospitalier à l'Université Paris-Cité, et Mme Farida Zehraoui, qui nous rejoint en visio. Elle est professeure des universités à l'Université de Tours. Et nous avons aussi le directeur de thèse, Jean-Baptiste Lamy, chargé de recherche à l'INSERM, et Kalima Sedki, maître de conférence à l'Université Sorbonne Paris-Nord. Okay. Et finalement, la raison pour laquelle nous sommes tous réunis ici aujourd'hui, nous avons la doctorante Nada Boudegzdame, qui est inscrite à l'Université Sorbonne Paris-Nord. Donc, je vous propose le protocole suivant. Okay. Donc, la doctorante nous fera la présentation de ses travaux de thèse pendant 45 minutes. Okay. Par la suite, les membres du jury donneront leur appréciation de la qualité du travail, de l'exposé, et aussi poseront des questions en rapport avec le sujet de thèse. Okay. Et après cela, le jury va se réunir à huis clos afin de délibérer et faire la rédaction du rapport de soutenance, du procès verbal de soutenance. OK, Nada, S'il vous plaît.
Hello, everyone. I would first want to thank everyone for being here. I would like to thank all the jury member for being here and the ones that have taken the time to read and have expressed interest in my work. So without further ado, I will be presenting my work on artificial intelligence-based method, machine learning, oversampling, and argumentation for smarter medical prescriptions. Recently, there has been a major leap in AI, and it can offer a potential for supporting healthcare. However, it's not always easy to apply it to medical field. Too many challenges. First, developing reliable predictive tools in medicine in terms of interpretability, the transparency of the predictions, and the explainability of the predictions. We also have to deal with conflicting medical knowledge. And so what would be the place of AI in the medical workflow where we have diverse clinical actors? A huge rise in public healthcare is polypharmacy. Polypharmacy is defined as taking 5 or more medication, which has several consequences leading to inappropriate prescriptions. In France, for example, more than 50% of elderly patients suffers from inappropriate prescriptions, leading to drug-and-drug interactions, contradictions, increased risk of adverse events, as well as leading to hospitalization as well. And we have economic consequence with direct cost of more than 500 million euros in France alone. A medication review is a promising solution. The process is the patient would go to consult the pharmacist for a medication review. It will optimize the drug order and delete inappropriate prescriptions and write a summary of the recommendations. Secondly, the doctor will assess the review and then modify or revise the drug order. This has demonstrated many benefits, such as reduction of emergency hospitalization by a third, and also savings per patient per year. However, its adoption is limited to lack of time and lack of training, and also communication difficulties between the pharmacist and the GP. To address the challenges of supporting medication review, the ABIMED project has been launched, which is an honor project that aims to design and evaluate clinical decision support system dedicated to medication review and polypharmacy management. My thesis is funded by this project and aims to extend it by first adding machine learning for predictive risk modeling, and also intervene during the post medical review discussion with collaborative reasoning. So the objective of our thesis are the following. The first axis focuses on developing predictive models for identifying adverse events. And the objective is to address the many challenges, mainly imbalanced classes that are frequently encountered in medical data. And the second axis focus on addressing the collaborative dimension of medication review, aiming to design and evaluate an argumentation solution for facilitating medical medication review. First, our first initial objective was to predict hemorrhage risk from patient drug order. For that, we used a training data set from Mimic, where we faced a highly imbalanced data set where only 3% of patients were at hemorrhage risk. Sorry, can I try to maybe so we can see? It's fine. So as I was saying, the highly imbalanced data comes with many challenges. Mainly, a machine learning model learned to predict the majority class, meaning to predict hemorrhage at the expense of the minority class, so hemorrhage risk data points. This will lead to imbalanced predictions. There is many method for addressing class imbalance. Here mainly we're gonna talk about the one that will intervene during the training process, which is cost-sensitive learning, which is the reweighting of training instances, weighting of the loss in order to attempt to reimbalance the classes and as well as threshold moving. Other technique is reassembling technique that aims to rebalance the distributions of data point before training. The advantage of this method is it will improve the model ability to learn accurately to classify both classes. Oversampling is the generation and duplication of data samples from the minority class in order to reimbalance the final data set before training. One of the most common oversampling technique is smooth. Smooth identifies the k nearest number to a point of the minority class and then will create and find all the neighboring key neighboring point from the minority class and will create synthetic sample on the line joining point and its neighbor in order to create data points that are similar in feature and characteristic to the other minority class data points. However, in literature, many challenges have been discussed about oversampling. The first being the model over reliance on inflated minority class, leading to the neglect of the majority class and reducing the generalization ability, leading to minority class bias. We also have data consistency. For example, we will have a patient that is 2 years old and is 200 kilograms, which is not as a data representative of real data. Secondly, we have mislabeled samples. So when we're creating or synthetic samples, these samples can be not related neither to the minority class or neither to the majority class. So there are noise samples. And we also have the problem of distort distribution, since synthetic sample can distort the original data distribution by producing overly similar sample, reducing the overall diversity of the data set, which limits the model ability to learn from a wide range of real problems. So let's go back to our initial task, predicting hemorrhage risk. Sorry, I don't know.
Maybe if you click on the, top left.
This one?
Yeah, that one,
This
yeah.
one. Yeah. Okay. This is better. Thank you. So we'll go back to our initial learning task, which is predicting hemorrhage risk. We use several methods for handling class imbalance. We evaluated through many machine learning algorithms, mainly neural network, random forest, logistic regression, KNN, Gaussian NB, and so on. We also use an autoencoder to reduce the dimensionality and also uncover underlying patterns. As for class imbalance, oversampling were used. We used several, smooth and its variant, and we also used GIN. And the second method for class imbalance, we used sensitive learning by class weighting and weighting the loss. Our result for predicting hemorrhage risks were at F1 score of 87% when testing it on oversampled testing data. So this begs the question, can hemorrhage risk be truly predicted with such remarkable accuracy only using prescription data alone? So to investigate furthermore, we tested the performance of the model on original data that does not contain oversampling samples, and now the F1 score is at 15%. So we formulated the hypothesis, are we learning to classify or to detect synthetic data? In other terms, a machine learning model trained on oversampling data tend to learn to detect the synthetic nature of data rather than predictly classify the minority class. Here, we have a class of moderate imbalance data. As we can see, a few data points need to be added in order to reimbalance the data set, and we can see on the distribution part that we only have few synthetic data points. Whereas when we are in case with highly imbalanced data, we see that the number of synthetic samples that need to be created in order to reimbalance the data set are big. And therefore, when we go and see the distribution of the resample data, when we go see minority class, we will find only fewer original data, which is kind leading to a confusion between the minority class and the synthetic data. In order to confirm this hypothesis, we trained a neural network to classify oversampled data to determine whether they are original or synthetic with several variation of smooth, borderline smooth, smooth and aliasing. And we see that the results here are suggesting that the model is easily able to detect synthetic data. We have an average, let's say, 92% F1 score, meaning it's super easy to predict the synthetic nature, and our hypothesis is confirmed. Several existing work have discussed it, the limitation of oversampling, but none explicitly mentioned or qualified learning the synthetic nature of data. So if synthetic data can be detectable, can we generate better synthetic data? So we propose the following algorithm. First, we will generate using any oversampling technique synthetic data, and then we will take the minority class that now contains original data and synthetic data, and we will relabel them, train a neural network to detect the synthetic data. The ones that were detected as synthetic are unrealistic and will be deleted. Then we'll check, is our final data set balanced? Here it's not balanced yet, so we go back and we regenerate synthetic data, and then filter the unrealistic synthetic data until we are able to have a balanced data set which is filtered only containing realistic synthetic data. Another approach to alternative classical oversampling technique are GIN. GIN are generative adversarial networks that are two neural networks that here comes to compute The generator will generate synthetic data from random noise, and the discriminator will distinguish real samples from the generated samples. Therefore, D will learn to detect fake samples, and the discriminator is used to train the generator. However, we can observe that sometimes the generator can learn to fool the discriminator. And therefore, we will use this method to compare it to our filtering method to see whether this approach or the approach of directly deleting synthetic samples is better. So for our experiment, the objective was to assess the generalizability and applicability across different word scenario. As you can see, we have different domain, and also we use data set that have diverse minority class ratio going from as low as 0.17% to as high as 32%. For hemorrhage risk predictions, the initial F1 score was at 62, and when using smooth as an oversampling technique, we see a severe decline in the performance. Now the F1 score is at 12%. However, only by filtering the unrealistic synthetic data that was generated here, we have a better score, which is now at 69, and it's better of the score to the first original score without using any oversampling technique. We also observed that each time we filter the unrealistic synthetic data, the performance improved to each point. So our filtering seemed to improve the prediction performance, but we will see the result of the rest of the data set. We see when for credit card fraud having the lowest representation of the minority class, the initial F1 score was as 23. When using smooth, it went down and to 0.000442. And when using filtering, the score went as high as 91% F1 score. GIN also has improved the result, but not at the same rate. And we see that our method excelled when working on highly imbalanced dataset. As for student dropout prediction, where we have balance of 32%, we see that the initial score of F1 score was 61, and then when using borderline without filtering, it went up to 80. When using the filtering, it improved also and went to 85%. However, we gained 3 points when using GIN, and we can see that GIN can be affected when the minority class is sufficiently represented. As for car insurance claim on small data set with limited instances and features, limited improvement are observed, and the challenge lies in running out of possible synthetic sample to effectively balance the classes. Across all the result, we see that our proposed filtering oversample method demonstrated more stable and consistent performance improvement across all the evaluated data set. Now we observe, let's try to discuss the difference between GNN and the proposed filtering method. So GNN are generate synthetic sample, whereas our technique does not generate synthetic sample. It use any existing oversample technique to create to generate synthetic sample. Therefore, it's a generic method. The evaluation of the quality of the synthetic data is implicit by training the discriminator, whereas in our technique, we have explicit identification of unrealistic synthetic data, and we explicitly evaluate the quality of the synthetic sample. And last but not least, we see in GIN the detectability is addressed indirectly, whereas we address it directly by filtering once the unrealistic synthetic sample once identified. So to conclude this first act, we first identify the problem of model training on synthetic data, predict the synthetic nature rather than predicting the minority class. We have proposed a quantitative method for assessing the quality of synthetic data and propose a generic filtering oversampling method that selectively remove unrealistic data. And we evaluate this method that performed consist improvement of performance on several word data set, and we see an improvement in the generalization capabilities. Now going back to the medication review, we see that in the process, when the GP gets the summary of recommendation addressed by the pharmacist, he or she revised and modified the drug order. Therefore, the GP retains the final say in implementing the recommendation of the pharmacist. And since there is communication difficulty mainly due to the lack of effective tools to support consensus building, many pharmacists' recommendations go unadopted. Argumentation can support this collaboration process, but how? Firstly, what is argumentations? Argumentation presents argument to support or oppose a position, a decision, or an opinion. It aims to convince or justify rationally. It handles conflicting information and conflicting opinion throughout effective logical reasoning. It also evaluates the argument in order to identify the accepted arguments and then rank them. We have an example here of a hypertensive patient that is currently treated with diltiazem, and the question is whether to add bisoprolol or to describe an ACE inhibitor. We have the first argument being bisoprolol is an effective option for managing hypertension, therefore it should be prescribed. The second argument is ACE inhibitor are a safe and effective option for managing hypertension, therefore it should be prescribed. The third argument is saying bisoprolol is contradicted with diltiazem due to the risk of bradycardia. And the fourth argument, we see that the patient has diabetic and ACE inhibitor are not clinically recommended, therefore it should not be prescribed, and we have an attack relation here. When using the argumentation, this is an example of the Dung argumentation framework, and when using the semantics, we find that the accepted arguments are argument 2, 4, and 3, and therefore here the solution, the best solution using Dung is to prescribe an ACE inhibitor. So we want in this act to incorporate argumentation strategy for medication review in order to facilitate GP and pharmacist collaboration and also increase the acceptance of the pharmacist recommendations. We will do so by first selecting the appropriate argumentation framework. Since there is so many for clinical decision support, we will structure the medication review with the selected argumentation framework and then implement a collaborative dialogue platform for medication review using the selected argumentation framework, and finally evaluate the platform with real clinicians. Argumentation framework has been applied to clinical decision making, where there is several clinical decision support systems that integrate argumentation that have been developed. However, non-prior work, to the best of our knowledge, has focused on the selection of the most appropriate argumentation framework for clinical decision support system. So our goal is to find which argumentation framework provides an explainable and actionable argumentation framework for handling complex medical decisions. We will do so by first reviewing the major argumentation framework, define criteria specific to clinical decision support system, and finally perform a comparative analysis of the major argumentation frameworks that exist. Since the first introduction of Dung's argumentation framework that represent attack relation only, several other argumentation framework has been created. We have PAV that incorporates preferences between argument, VAV that assigns social values to arguments. We have BAV that model both attack and support relationship, and WAF that introduce weights to the attacks. We also have DFQID, which is a quantitative method that structure debate and compute the strength of the solutions. To determine the most suitable framework for clinical decision support system, we have defined the following criteria tailored to the specific need of clinical decision making. Firstly, we need to clearly distinguish clinical problem, their candidate solution, and the associated argument. So we need identification and representation of problems. In clinical settings, attack relations and support relations are not the same. So the lack of attack does not constitute a support relationship, and an attack of an attack does not support is not a support relationship. So this argumentation framework, we must both models the attack and the support relationship, and also account for the differing importance of clinical arguments by having a weighted argument and relations. And finally, a quantitative ranking of solution. Why is that? Since in clinical setting, the best solution might not be feasible, therefore having a quantitative value to each argument will help us have an ordering to find the next best solution to implement. So here we have the comparative analysis of the argumentation framework, and the clear winner here is DFQID. It allows two models, attack and support relations, structure the problem into the medication review, any problem into issue, position, arguments. It also represent the weight of arguments and present the strength of argument as a quantitative value. So let's dive in more into DFQID and what it is. Disconnectivity, free quantitative argumentation debug framework structures dialogue and debate around three elements: questions, solutions, and attacks. In the context of medication review, questions are the problem that need to be treated. Solutions are recommendations or intervention on the drug order, and arguments will either support or attack solution or support or attack themselves. It also provides an algorithm to quantify the strength of the potential solution by many steps. The first step being aggregating attack and support. This aggregation function will multiply attackers and supporters into a single influence value. Then the second step is to balance attack and support. This combination function will compare the aggregated attack and support to determine whether the score will increase or decrease. Using both aggregation and combination function, we can compute the final strength of each argument. Once an argument strength is known, meaning how strong of a reason it is, we can compute the strength of the solution by the same way as we did for computing the argument strength. Here we take the previous example about the hypertensive patient. We had the Jung argumentation framework represented here as we see, and on the right side we see when you is in the FQID we have more clear per se a graph when we have what is the problem, the solutions, and the supporting and attacking argument. And we can see that the preferred solution is ACE, and the strength is calculated strength is 0.75, and therefore is the preferred solution. Now that we have selected an argumentation framework, the next step will be to integrate the FQID into a clinical decision support system, since to now no work has integrated the FQID into a clinical decision support system. And we will structure medication review using the FQID. So, when structuring medication review using the FQID into a collaborative dialogue problem, we have defined several categories of problems. That can be drug-related problem rated by patient or identified by clinicians. We also have solutions that are recommendation or intervention on the drug order, and the arguments that support or attack these solutions or recommendation. We have several arguments: contraindication, drug-drug interaction, drug dosage, and stop-start guideline that are already built into the ABIMED existing system. And we also propose that clinician can add other arguments. The FQID, we have structured these elements into a formal ontology, and the FQID will systematically rank all the potential recommendations. Common sense vs formal reasoning. What do we want to say here? Clinician knows common sense logic. However, the collaborative dialogue problem must encode this logic. For example, the argument saying increase the dosage because the drug causes adverse event is an inconsistency. So we therefore have to explicitly define which argument can support a given solution. Possible solution for this is the use of formal ontology. But how? by using restrictions that allow the defining how individuals of a class might be linked of individuals to other classes. Restrictions specify which argument can attack / support a given argument or solution, and which argument solution can be attacked or supported by a given argument. So we have defined a correspondence table between the argument and the solution in order to define the attack and support relations into a big graph, as you see, but we will take only a smart part of it to show here, and this table of correspondence was used to automatically generate these restrictions. So a restriction would be adverse event can only support stopping the drug, increasing the dosage, or replacing the drug. So the argument adverse event cannot be a justification for increasing the dosage, because using this ontology, only 3 solutions can be supported, and increasing the dosage cannot be supported using this ontology, which will allow to ensure the consistency throughout the discussion. Any medication discussion between clinicians are structured and displayed as an argumentation graph, and will be encoded with additional visual improvement that we will see during the demonstration of the platform. So we'll take the clinical case of a 78 male patient taking several medication, having several medical conditions, and the aim is to find, the question is which hypertensive treatment. Reflecting on real cases of medication review in real life, pharmacists and GP do not have similar information and therefore have incomplete asymmetrical information about the patient. So now we go to the demonstration. Can I? Sorry, I will. Mhm. So, good. Okay, here we are. And we can do it just a second. Yes, we have it here. However, for me, it's gonna. Where am I? Sorry, I'm here. So platform, we will enter as the pharmacist here, and we will, before seeing, we will go check the patient case here. This is the patient, this is the AbiMed platform. We will go and see, we have many, we have here an interaction between drug-drug interaction between atenolol and talmilizine. Maybe zooming will be better. Yes. And when we go to the stop and start guideline, we see that there is a rule that have been triggered. And also we have checked for the drug-drug interaction between the tamsulosin, and it is a drug-drug interaction to be taken into consideration. We should also sign in as the GP as well. And as we can see that the medication review process has already started, maybe they are in a hurry. And we see the problem that was identified by rule of stop-start guideline regarding atenolol with the rule stop and start 5. A possible solution is no change and keep atenolol. But we have a drug-drug interaction between tamsulosin, as we just saw, and atenolol. Since it was to be taken into account, the weight of this argument is 10%. And we see that we have another argument, beta blockers are not recommended as first intention treatment in essential hypertension, and it has a weight of 505. And since we're in a hurry, we see that there is another solution that has been proposed, which is to replace atenolol with amlodipine. And the arguments added by the doctor is saying retry calcium channel blocker while checking for compliance. What do you mean retry? So the pharmacist can ask and the pharmacist, why retry? Because he doesn't, and the pharmacist didn't know that he tried it before. So the pharmacist tried several years ago. So the pharmacist is now not convinced about this drug and now will try to therefore see other. So the pharmacist has proposed to replace atenolol with the hydrochlorothiazide, and we will observe now if the rule stop is not triggered. Yes, with the changement is not triggered, and therefore we will add it as a solution. So we will replace atenolol with and the argument would be bibliotic references that they are recommended as first intention treatment. And the weight of that will be 7. And we can also check here for the drug-drug interaction with this new medication, and we see that we have a drug-drug interaction. So zoom in less will be so it concerns hyperkalemia, and when we check for adverse event, we see hyperkalemia as well. So we can the doctor will now add an attacking argument. Hyperkalemia, which will have the weight depending on the interaction, and is second level. So we will keep the weight as 0.5, and we add it. Here we see that the preferred solution is now 17%, and it's highlighted the width of each represent the weight of each argument. We have facility in adding and in adding arguments, either on clicking on them. We have by using the ontology restrictions, several different arguments that depends on what an argument can support and what an argument can attack. So can we now go back to the presentation? Yes, we can. We can have a later on discussion about this case. So this was the presentation of the platform that was developed, and we aim to evaluate the platform before saying it facilitated clinician reaching consensus. The evaluation method was to use 2 case studies conducted by a GP and community pharmacist. The platform was demonstrated to clinicians before evaluation, and then they were placed in a different room and remotely collaborated through the platform chat and the argument graph. And the clinicians also received partial information reflecting the real medication review practice in real life. The key findings of this evaluation is that consensus was reached in both case study, and the preferred solution that was identified by the platform matched the clinician final decision. The hidden information has successfully surfaced. The clinicians asked clarifying question and did not realize that they had asymmetrical information. However, for the argument graph usage, many arguments were discussed in the graph instead of formally entered due to the time limit that we defined for each case. About user feedback and limitation, the clinicians were enthusiastic for complex cases and suggested many other applications. Many limitation has been identified, saying that the platform requires 10 investment for detailed argument entry, and as for the user interface, several improvement needed were suggested by the clinicians. Several clinical decision support systems for medication review have been developed. However, to the best of our knowledge, none have incorporated argumentation. The limitation of the current collaborative dialogue system is that it requires significant time involvement from clinicians, and for complex cases, simultaneous discussion between clinicians is necessary. To conclude this axis, a collaborative dialogue platform is an argumentation-based system that supports pharmacists, GP collaboration in medication review by visualizing medication review discussion as a graph and visually translation the reasoning behind the decision making. It evaluates potential solution and provide transparent decision support, since accepted solutions are backed by argument. It ensures logical consistency throughout the discussions, and mainly it encourages clinicians to clearly articulate their argument, especially in cases when we have asymmetric information. The platform is particularly useful for complex cases with no obvious solution. This work positions itself at the intersection of computer science and medicine. However, the results presented here are not limited to medical domain. Class imbalance is a common problem in anomaly detection and can be applied to other domains. The collaborative decision-making platform could be applied to other domains with minimal changes. As for future directions, we aim to extend our classification from binary classification to multi-class classification, as well as multi-label classification. We also aim to build an adaptive meta-learner that adjusts the training strategies dynamically to the dataset characteristics in order to develop quality metrics to detect issues such as overfitting and weak generalization. For the second axis, the main first one will be to conduct a large-scale evaluation with real clinicians and healthcare professionals. We aim to include the patient as an active actor in the decision-making process by representing their preferences, their value into the argumentation process. We also aim to adapt the platform by creating a web-based ontology editor to adapt it so that the collaborative platform can be extended to other domains without prior knowledge to coding. And we have to talk about LLMs. We aim to use LLMs as intelligent moderators and mediators in order to facilitate consensus reaches and conflict mediation, and also argument mining from the dialogue. And finally, we aim to combine these two axes by providing a hybrid predictive argumentation decision support. How? By using the scores for machine learning risk predictions as an argument in the collaborative dialogue platform. I want to thank you for your attention. I'll be happy to answer any of your question, comment, or counter argument. Thank you.
Très bien, merci beaucoup, Nada, pour l'exposé. Donc, nous pourrons maintenant passer à la phase d'interaction avec les membres du jury. Je proposerai, comme c'est l'usage dans beaucoup d'endroits, que l'on démarre avec les rapporteurs. Et je proposerai aussi de suivre l'ordre lexicographique des noms de famille. Et donc, si ça vous convient, je passerai la parole à un collègue